Hi there, and welcome to this video on applications of graphing lines. This video is a little bit different from my usual videos. There's no attached practice set, and this video doesn't really introduce new information so much as it looks at ways of applying information that either you've watched in these videos or you've covered in your class. As always, please give this video a thumbs up if you find it helpful and subscribe to the channel for more math content. Drop a comment, let me know what you think or if you'd like to see more videos like this one. So why is representing a relationship graphically a useful skill? In algebra, we tend to use three main modes of representing relationships. One is a table of points, one is equations, and the other is the graph. And a large part of the fluency in your math is being able to go from one representation to another. Graphs allow us to create and exploit pictures. Most of us are visual learners. We see things on the page. We respond well to pictures and illustrations. And graphs are the math way of taking an abstract relationship and making it visual for us. Here is an example. So suppose you have a spring. Probably if you're watching this video, you have seen springs. You've taken apart a pen, taken the spring out of the pen. You know what I'm talking about. You have a spring. Okay. And as you exert a force to pull the spring will stretch. So you can grab a spring if you got one around, or just picture it in your head. You pull on the spring and the spring begins to stretch. The more force you use, the more the spring stretches. And again, this is very, very intuitive if you've ever played with a spring of any sort. And it could be like pulling a spring. Some springs are compression springs where you would push down on them. But the idea that the more force you use, the more stretching or possibly compressing you can get out of the spring is something that we've encountered in our everyday life. So there is a mathematical relationship between the force you use and the amount of stretch that you'll get from the spring. Those are not random sets of numbers where you're going to pull on the spring, but who knows how much the spring is going to stretch. Like, you know that as you increase that pull, you increase that force, that the amount of stretch you get is going to also increase in a predictable way. So this is precisely the activity that some of my students did recently. I teach math classes, but I also teach some engineering classes. And this is actually a sample of one student's data. So I just took that data right off of the student's page. And let's take a look at what is in that table. So the left column shows how much force was applied to the spring. Students used a spring scale, which is a scale with a spring in it, and it's marked with units on the side. And so you can tell how much force you are using by reading it off the side of the scale. Force is measured in a unit called newtons, represented here by a capital N. So if we look at this young lady's work, you were looking at that left-hand column there, and she's got it labeled with force, and then she has the units there as well. So we're doing 0 newtons, 2 newtons, and so forth. The right-hand column shows the displacement of the spring. Displacement is a science word. It's actually a physics word. And it's related to the idea of distance, except it's got direction implied with it. So it's something called a vector. So displacement is another term for how much the spring is stretched. She measured the stretch of the spring in centimeters, represented by the cm. So in this right-hand column, we've got how much the spring was stretching in centimeters. And if you notice, when there was no force applied, there is no stretch. Okay, when 2 newtons worth of force were applied, then we got a stretch of 0.6 centimeters or 6 millimeters, and so forth. And each of these can be turned into an ordered pair. So we could have the 0.00, the 0.2, 0.6, and so forth. Students were tasked with plotting these points, finding the line that best fits their points, and then using the linear relationship to predict the spring stretch for more and more force. And so that was the activity that my students were carrying out in class. So recall how the coordinate plane works. All right. In math class, we usually just think in terms of X and Y axes. So you've got your horizontal X axis, I'm in the upper right corner there. And you've got, so that's a number line on your X axis. And then you've got the Y axis, and that's your vertical axis. But in application problems, we need the X and Y axes to represent the different variables in our situation. So application problems, which personally I think are where the math gets fun and interesting, like a whole lot more interesting than just X's and Y's. Those two axes actually represent the things in the problem. In this case, students use the x-axis for their force and the y-axis for their displacement. So instead of x and y, we now have force and displacement on the graph. And so it might look something like this. And I want to note a couple things about it. We have the x-axis and the y-axis. Now, in this example, they are scaled equally, but you do not have to do that. So there might be times where the numbers on one of your axes, say, go up to 100. Well, you don't want to do 100, like, yeah, that's going to be a weird shaped graph. And so you might decide to count by tens. You don't have to count by the same thing on the X and the Y, but once you decide what you're doing, you have to be consistent. Notice also that we have them labeled. So we know that the numbers on our vertical axis here represent the displacement in centimeters. So we got 1 centimeter, 2 centimeters, 3 centimeters, and then we have force and the unit used to measure the force going across the x-axis. So we have like 1 Newton, 2 newtons, 3 newtons, and 4, and so forth. And a well-done graph is going to be scaled clearly, and it's going to have the quantity and the units on it. Since this situation does not involve negative numbers, we do not need to show those portions of the coordinate plane. Now, when I made this, I did put it going to -1 and -1, just to show you that those other quadrants are still there. But in this particular example, like the spring doesn't stretch negative. Now, I mean, there are places where you might have that if it's the kind of spring that will both stretch and compress, but that was not what the students were working with here. Note that each axis should be labeled with the quantities and being measured and the units used. Okay, so let's look at her data when we plot it. So I went in and I actually plotted her data. So you can see the 0.00. This is the 0.2, 0.6, and so forth. So when 4 newtons were applied, the spring stretched 2 centimeters. Okay, and that's what it looks like. Notice a few things about this. First of all, the data is not a perfect line. Real life data points rarely are. In math world, when you are asked to graph a line, your points are in this perfectly straight line. In real life, though, they are not, because we do not live in a perfect world. However, we can see that the overall relationship of the data points is clear. They're not randomly scattered all over the coordinate plane. They are in a line shape. It's just not a perfect line, and that is very, very common. The line of best fit is the line that comes as close to as many of the points as possible. So one of the things my students had to do here was draw in by hand the line of best fit. And so they would take their ruler and they would put the ruler and they would try to find a line that would come as close to as many points as they could. It may go through some of the points, but the line of best fit doesn't necessarily have to go through any of the points. So if your points were kind of scattered above and below, your line of best fit could go straight through them and it wouldn't touch any of the points. Many, many times, though, the line of fit will go through at least a couple of the points, but certainly not all of them because they're not all on a line. Okay, so this is this student found her line of best fit here. Okay. And so what I did was I looked at the student work and I typed in what she got for her line of best fit, and then I went in and graphed it. And you can tell right there that that does not actually look correct. That does not look like the line that would come as close to as many of those points as possible. Her line of best fit was a little bit high, and this was due to her misreading a point on her own graph. So my students did not do their lines of best fit. Her line of best fit, let me put it this way, and I have it in a screenshot later in this presentation. You can see what she did. She actually put her line of best fit in a better spot. And then when she was coming up with the calculation for it, which is beyond what we're going to talk about in this video, actually made a mistake and read one of the coordinates wrong. So yeah, so she made like an error in that. So her line of best fit was sitting a little bit high. A better line of fit might be here, okay? And so I went through and I adjusted it, and notice a couple things about the line of best fit. This line of best fit does appear to go through 2 of the points. Okay, so it looks like it goes through 0, 0, and 6. I think that was 6, 3.5. It's sitting above 2 of these points and below these 2. And that makes it a pretty good line of best fit. A lot of graphing calculators will actually find this for you. So when you are at the point where you're using a graphing calculator, you can put the points in and say, hey, calculator, find the line of best fit for this, and the calculator will come up with a mathematical calculation for it. This one was just done by eye, as was the one that the student did. Now, once you have your graph, what can you do with it? In this activity, students were to predict how much the spring would stretch with 15 newtons of force. And it was a good question for them because the scales they were using only went up to 10 newtons. And so this is not something that they could measure. They were asked to do some calculations. We're going to save that for a different video. So what I'm staring at one of the students' work right in front of me. And so they had to take their graph and they had to do some stuff with it. And what I'll do when I've had a chance to record some more content videos is we'll come back to this problem. So if you're kind of coming at this after the fact, I'll try to link the second video to it, so you can find that in the description box. But at the time of this recording, said video does not exist, but it might by the time you are watching this. Okay, so how much will our spring stretch with 15 newtons? What we need to do is extend the graph a little bit. And so what I did here was I took that x-axis and I had it go out to 20. And then notice what I did with the numbers. Instead of numbering every single one, now I'm numbering just every other one, because otherwise it gets super, super crowded. So once you have your model, you can come over here to 15, so 15 newtons, and go up, and you can find that ordered pair, that location, and that looks like it might be about 8.8, 8.7, a little bit shy of 9. And there are ways that you can do this with the equations also. Like I said, we can save that for a future video. But that's what you can do with your model once you have it. So there's no practice set for this video, but I think closing out, there's a couple questions that are worth considering. So before you click out of the video, why might scientists or engineers need to predict the behavior of springs? Springs are in so many things, and we are not guessing. So when somebody puts a set of springs in your car, or in, I don't know, your microwave door or whatever, you've got your wind-up toy. Why do scientists or engineers need to be able to predict this? So we need to know what will happen to this spring under this set of circumstances. Second question, how do the skills of working with tables and plotting points help in solving problems like this? So that fluency that you build when it's just X's and Y's. So you're in sanitized math class, and then you pull out of your math class there and you get into a situation like this. What's the transfer of those skills over? I mentioned this earlier. Why do you think real life data is rarely a perfect line? I mentioned that real life data is not perfect. But why? Why isn't it perfect? If it really is a linear relationship, why isn't our data coming out perfectly? And for this fourth question, to play teacher, this is the student graph that goes with that data table from earlier in the lesson. Can you spot the error on her graph? And there actually is enough information written here. So what she was doing is you can see the data points, and she plotted her data really well. You can see she's got the axes labeled. This looks good. And her line of best fit also is good. But her equation had an issue. Take a look at that and see if you can find what was wrong. So play teacher, play sleuth. This is what we do with student work all the time is something goes wrong, we got to figure out what it is. And here's one to try on your own. Take this data. This is from same activity, a different student. It might have been a similar spring because it is similar data. My students actually did have a variety of different springs, but I pulled some of the students that I think had like they took good measurements with it, and see if you can do it. There's no answer key to this because where you put your line of best fit could vary, but you should be able to come up with a reasonable answer. And I will tell you that the student who used this data had 11.25, so 11.25 centimeters is what he got for his. So, and again, he is not perfect, just like the other student wasn't perfect. So you can kind of play around with that. So I'll put that here. The student answer was 11.25 centimeters. So play around with this. See, do you think he was right? Do you think he was wrong? And see if you can do one. As always, like and subscribe if you found this video helpful or interesting. Leave a comment, let me know what you think, and I will see you in the next one.